Okay, log rules. So we will look at some notation, inverse identities, three rules, expanding and contracting logarithmic expressions, and change of base. So notation, ln stands for natural logarithm or base e logarithms. So ln of x is log base e of x. Base 10 logarithms, if there's no subscript, that means base 10. For every other base, we include the base as a subscript, so base 7 logarithms are written log base 7 of x. Okay, inverse identities. So what we saw is that exponential functions and logarithmic functions are inverses. The fundamental rule of logarithms and exponentials is the transformation between the two. So an equation, b to the x equals m, that's its exponential form. The logarithmic form is log base b of m equals x, and we can transform from one to the other. So b to the x equals m means log base b of m equals x. So we can transform from logarithmic equations to exponential form, and then we can solve them. So a, x equals log base 2 of 8. That means x is the number that 2 is raised to get 8. Right? So base becomes there. The base of 2 becomes that. The x becomes the new power. So this becomes the power. The thing inside the logarithm gets isolated by itself on the other side. And we know that that means that x equals 3 because 2 cubed equals 8. So for b, x equals log base 4 of 16. That means 4 raised to the x. So 4 raised to the x equals the thing inside the logarithm. And that means that x has to equal 2 because 4 to the x equals 16. We raise 4 to the 2 power to get 16. So that's log base 4 of 16. So if we have x equals log base 7 of 1 over 49, we can convert that to an exponential equation. 7 to the x equals 1 over 49. And that means x has to equal minus 2. Note that we have a fraction here. 49 is 7 squared, but it's in the denominator, so x is minus 2. For d, x is log base 25 of 5. So that means we want to take the base to the x power, 25 to the x, and that should be equal to whatever's inside the logarithm. And now here we're going from a base to a smaller number, so that means we're taking a root. In this case, x equals 1/2. The square root of 25 is 5. So problem E, similar thing. If x is log base 36 of 6, 36 to the x is the thing inside the logarithm, which is 6. And so again, x is 1/2, because 36 to the 1/2, square root of 36 is 6. And then finally, part E, x equals log base 8 of 1/2. That means we want to number x so that 8 to the x is equal to 1/2. But we remember that 2 cubed equals 8. So 8, the cube root of 8, which is 8 to the 1/3. Maybe erase that so I can write it better. 8 raised to the 1/3 power equals 2. So 1/2 is 1 over 8 to the 1/3 power. That's 8 raised to the minus 1/3 power. So x is minus 1/3. That's the power that 8 is raised to get 1/2. So we think about logarithms as being powers, they're exponents. X equals log base 2 of 8. That means what power do we raise 2 to get 8? And 2 to the x equals 8, x equals 3. And you'll see problems like this on my math lab, questions like find log base 2 of 8 equals calc without a calculator. You can set up x equals log base 2 of 8, convert to exponential form, and see how that goes. But you can also convert exponential equations to logarithmic equations. So for a, so our fundamental rule again, b to the x equals m can be converted to log base b of m equals x. So 3 squared to the 9, that means 2 is the power that 3 is raised to get 9. Right? So the base is 3, the power is 2, and 9 is the number that goes inside the logarithm. So for part B, 1/2, that's the power, is the power that the base, which is 121, is raised to get 11. C minus 3 is the power that 6, the base, is raised to get 1/216. All right, so the pattern hopefully is becoming a little bit clearer. The base goes down here, and now the power gets isolated by itself, and whatever the number is that goes inside the logarithm. For D, 5x equals 20. Then x is the power that the base, which is 5, is raised to get 20. And we know that 5 to the 1 equals 5. 5 squared equals 25. So 20 is in between 5 and 25. So x is going to be between 1 and 2. And that's the intermediate value theorem again, right? The power that 5 is raised to get 20, it's got to be bigger than 1, but less than 2. Likewise, whatever x this is, it's going to have to be bigger than 3, because 7 cubed is 343. And I don't know that offhand, I just calculated it. And 4. So for E, the power is the logarithm base 7 of 350. And I know that 7 cubed equals 343. So whatever x is, whatever that power is, it has to be between 3 and 4. Because 7 to the 4th is 2100 something. And then F, 4 to the x equals 2. That means x is the power that the base, which is 4, is raised to get 2. And remember that 4 to the 1/2 equals 2. So x here is 1/2, which is square root. So that's the fundamental rule. We can use that to solve some of these equations. 400 at 6% annual interest compounded continuously. How long to wait for account to grow to 600? So compounded continuously, that means we're using this formula, PE to the RT. And remember that E is a number, it's about 2.71, but your calculator knows what it is, so you don't need to put that in. So what are the values that they give me? A is the amount in the future, so that's my $600. P is the amount that is being invested, the principal, so that's 400. R is the interest rate as a decimal. And T, we don't know, right? We're being asked to find how long. So if we plug everything in, we get 600 equals 400 e to the 0.06t. And we can't quite use the fundamental rule yet on this because we need to isolate the exponential term. So we'll divide both sides by 400 first. That gives me 6/4 equals e to the 0.06t. And a little bit of simplification makes that 3/2 equals e to the 0.06t. And so now we can use the fundamental rule because we have a base, which is e, and a power, 0.06t, equal to some number. So log of 3/2 equals 0.06t. And recall log base e is written as ln for logarithm natural, which is French for natural logarithm. So log 3/2 equals 0.06t. Divide both sides by 0.06. And you can solve for t. I should have here somewhere. And that's about 6.78. And keep in mind that 0.78 is about 0.75, 3/4. So that's 6 years and 9 months, more or less. That's how long Jane has to wait for. So we can solve these exponential questions and these questions about when using logarithms in the fundamental rule. We get 2 more identities because logarithms are exponentials and exponentials are inverses. So our composition rule about inverses, if f of x and g of x are inverses, then f of g of x equals x, g of f of x equals x. Right? And remember that an inverse right? So for example, if we had squaring function and square roots, 3 goes to 9, here y equals x squared. This is the function. Going backwards is the inverse function. And if we just do one and then the other, if we do the function and then the inverse function, we just come back to where we start. So our two inverse identities are as follows. If f of x is b to the x and g of x is log base b of x, what does that mean? Well, f of g of x means put the function log base b of x in for x in this formula. But because we know these are inverses, we know that this has to be equal to x. So that gives us x is b raised to the log base b of x. This is a useful and interesting thing because, for example, any number, we could say 7, is any other number, say 10, raised to some power. And what that power is the logarithm of that number. So if we think about the graph of y equals 10 to the x, seven is some y value. There's some x value that goes and gives you 7. And what that is log of 7. So 10 to the log of 7 is equal to 7. And likewise, g of f of x means take g of x, which is this function, and put in b of x for x. And so we have that. So those are two identities for logarithms. So these are the inverse properties. So that allows us to calculate things like this. Log base 14 of 14. Remember that 14 is raised to the 1 power. So same base and number in there, so that's just 1. Log base 14 of 14 cubed. Same base here and here, so that's just 3. 14 of log base 14 of 3, for example. Same base here and here, that's also just 3. And that allows us to calculate some of these things. Log of 100, keep in mind that if we have a log without any subscript, that means we're thinking base 10. 100 is 10 squared, so same base, 2. And that's the power that 10 is raised to get 100, right? 10 squared is 100. E to the ln of 32. Remember that ln is log base e of 32. Same base, that gives us 32. Natural logarithm of e squared, right? That's log base e of e squared, matching base, so that's just going to be 2. So this gives us a nice way to solve some equations, right? If we have b to the x equals b to the y, then log base b, we can just take log base b of both sides. And then we can use that identity. This whole thing is just equal to x, and this whole thing is equal to y. So if these two things are equal, that means same base, that means your two exponents have to be equal. So how can we use that to solve this equation? Where the same base is 10 on both sides. So that just means I need to equate the two exponents. 2x plus 1 equals 3. And then we can solve that by subtracting a 1 from both sides and then dividing by 2. So likewise, if we have log base b of x equals log base b of y, then we can use both as powers with the base of b. And then we know this by the inverse identity is equal to x. This is equal to y. So if we have two logs with the same base, if the logs are equal, then the things inside have to be equal. So log of 3x plus 1 equals log of 7, right? Same base, this is base e, that means 3x plus 1 must be equal to 7, subtract a 1 from both sides and divide by 3, and you get x equals 2. So useful ways to be able to solve logarithmic equations. And now we have some rules, a product addition rule, a quotient division rule, and a power coefficient rule. So remember that, as we saw before, if we have a base times the same base, then we can add the exponents. And that means we can go one way or the other, remember? So this is very similar, right? Because it connects multiplication to addition the same way that this does. So why does this rule work? Well, if we think about b to the x, and we'll say just 10 to the x for b. So take the base b 10. We know that 2 and 3 and 6 all have, if you think about them as being y values, they all have corresponding x values. So 10 to the log base 2 equals 2, 10 to the log base 3 equals 3, 10 to the log base 6 equals 6. What I want to say is that these two multiplied together gives me 6. These two added together give me log of 6. So why is that? Well, 2 times 3 equals 6. I can rewrite that because 2 is equal to 10 to the log base 2, right? So 2 is my output. 10 raised to the log base 2 will give me 2, times 10 to the log 3 equals 10 to the log of 6. But these are the same base, right? So we can use this rule. And now we know if we have the same base and they're equal to each other, then the exponents must be equal. And log base 6, of course, is log base 2 times 3. So that gives us this thing. Multiplication inside the logarithm can become addition outside of it. And it rests on the fact that every number can be written as some base raised to a power. There's nothing particularly magical about 2, 3, and 6. You could just take m and n and m times n. And there's nothing particularly magical about the 10. You can just use whatever b you want. So what does that mean about dealing with logarithms? Log base 17 of 34. We can break 34 into a product. Oops, it's not 2 times 34, it's 2 times 17. And now with this rule, if we have a product inside of a logarithm, we can break that into two logarithms, log of the first thing plus log of the second thing. So log base 17 of 2 plus log base 17 of 17. But we know that this is equal to 1, right? Because it's the same base raised to the first. So we can rewrite log base 17 of 34 as log base 17 of 2 plus 1. And then we can also contract things because these rules work in both directions. So log base 3 of 7 plus log base 3 of 4, same base. So that means we can condense it into one logarithm by multiplying the two things inside the logarithm. Okay, so similar to this, we have a quotient subtraction rules, right? And this is tied to the idea, which we've seen, is that b to the x divided by b to the y, you subtract the exponents, right? Remember that logarithms, you should think of them as being powers, right? So this is a logarithm, this is a logarithm. We divide, we subtract the logarithms. So again, 6 over 3 equals 2. Same kind of argument that we had here. Every number is, say, here we'll take b, take my base to be the number e. Every number is e raised to the something, right? 6 is e to the natural logarithm of 6. 3 is e to the natural logarithm of 3. And 2 is e to the natural logarithm of 2. So if we rewrite 6 over 3, that's e to the natural logarithm of 6 divided by e to the natural logarithm of 3. And that's e to the natural logarithm of 6 minus natural logarithm of 3. And that's all up in my exponent. But 6 over 3 is also equal to 2, which is e to the natural logarithm of 2. So these two things have to be equal to each other, right? But if these two things are equal to each other and they have the same base, then that means their two exponents have to be the same. But we know that 2 is 6 over 3. So if we have a quotient, 6 divided by 3, we can break it up into two logarithms, log of the top minus log of the bottom. So we can expand this one. Log base 5 of 25 over 3. We have a quotient inside the logarithm. So that means we can break it into two logarithms. Oops. Remember that log base 5 of 25, 25 is 5 squared. And so this whole thing, right, same base, this is just going to be equal to 2. And so there we've done some simplification for that. And we can contract it if we have two logarithms with the same base, with one subtracted from the other, so they're both base 7. We can combine that into one logarithm, base 7, log of this divided by that. So we divide those two things. Okay. Now finally, the power coefficient rule. Same kind of thing. This is dealing with the idea that b raised to the x raised to the y is the same thing as b times x to the y. So we use this in showing that. So same kind of thing. If b is any base, we know that 2 is b, whatever the base is, log base b of 2. And 8 is b raised to log base b, whatever that is, of 8. So 2 cubed is b to the log base b of 2, quantity cubed, that's a 2. And then I'm using this rule, that's b raised to the power of 3 log base b of 2. But 8, which is the same thing, right? 2 cubed is 8, that's just b to the log base b of 8. So since 2 is equal to 2 cubed is equal to 8, and this is equal to 2 cubed, well, this whole thing is equal to 2 cubed, this whole thing is equal to 2 cubed, what we get is b to the 3 log base b of 2 equals b, whatever our base is, equals log base b of 8. So 3, we put a little line there to divide, just to separate my calculations. So same base, that means this has to be equal to this, or 3 log base b of 2, since 8 is equal to 2 cubed. So what's the upshot here? The upshot here is that the power can come out front as a logarithm, or a coefficient out front can go into the logarithm as a power. So log base 2 of 25, we can rewrite 25 as a power. And then this power can come out front as a logarithm. 2 log base 3 of 4. This is a coefficient, so it can go into the logarithm as a power. And of course, 4 squared is 16. Okay, so what we can do then is we can take really complicated looking things and we can contract them or expand them, right? So we want to expand this as much as possible. We want to start with the product addition rule or the quotient subtraction rule. So we want to break this apart as much as possible. I have a numerator and a denominator. So quotient subtraction rule, that tells me that log of 100 x squared y cubed over 7z to the 5th is log of the top minus log of the bottom. And now I have multiplications, 100 times x squared times y cubed and 7 times 5. I'm going to put a bracket around this because I'm going to expand this, and I need the minus sign to distribute. So now I'll do the addition, product addition rule. Log of 100 x squared y cubed. So this whole thing is equal to this, which is equal to log of 100 plus, so all my multiplications become additions. And then separate logarithms, and then minus inside of here, I have another addition, I have another multiplication inside my logarithm. So it becomes log of 7 plus log of z to the 5. Great. And now I can use the power coefficient rule. Log of 100, there's not much I can do with that right now, but I can write this as log of 10 squared. 2 is a power, so that can come out front as a coefficient. So 2 log x. 3 is a power, so 3 log y. And then minus log 7, there's nothing I can do with that. Plus, here's a power, so that can come out front as a coefficient. So I'm not applying a rule here, but I know that, remember, log without a base means we're doing log base 10. So log base 10 of 2, that's just 2, because same base, then we just get the 2 out there. And then we have a 2 log x plus 3 log y. We don't know what x, y, and z are. They're just some positive numbers. And then minus log of 7 minus 5 log of z, right? And this minus sign distributes to both of them. Both of these terms came from the denominator, so they both pick up that minus sign. So now we've expanded that as far as we can. And so that's an expansion. Right, same thing here. Ln is log base e. So we can split this all up. Quotient subtraction rule tells me that this becomes ln logarithm of the top minus ln of the bottom. We want to keep track of the fact that square root of x is the same thing as x raised to the 1/2 power. So we break up the quotient, and then we do the product addition rule. So we get a multiplication here, and a multiplication here, and a multiplication here. Remember that all this came from the denominator. It's all going to need a minus sign. So we get natural logarithm of e cubed plus natural logarithm of x to the 1/2 plus natural logarithm of y cubed minus natural logarithm of 13 plus natural logarithm of z raised to the 4th power. And then we can do the power coefficient rule. This we'll just leave by itself for the moment. 1/2 log of x plus 3 log of y minus log of 13. And I'm going to distribute this minus sign here, and we'll get 4 natural logarithm of z. So what about this thing? Well, you can't think of this as just take the 3 out front as 3 natural logarithm of e. Remember that ln is log base e. So log base e of e cubed, that'll just be a 3. That's one of our inverse rules from earlier in this lecture. It's going to make this 2 a little tinier. And as you do more and more of these, you'll be able to recognize the patterns that are going on here. Everything that started out in the denominator will end up with a minus sign. All the powers will end up as coefficients, and then you just have sort of logs of things in there. So we can contract things. So we want to contract this as much as possible. The base here is b. So keep in mind from our inverse rules, 2 is equal to log base b of b squared, right? And we use that sort of up in that case as well. So we will use an inverse rule to rewrite this as log base b of b squared, that's my 2, minus log base b of x plus 5 log base b of y minus 3 log base b of z. And so to sort of go backwards from what we did up here with expansions, we're now going to do the power coefficient rule. We have a log base b of b squared minus log base b of x. There's no coefficient there. plus, now this 5 can go in as a power because that coefficient becomes a power, and this 3 can go in as a power. So, quotient subtraction, power addition rules, like PEMDAS or BODMAS, do it left to right. So we'll start with these two. It's a subtraction. So we get one logarithm, same base, which is b, and the b squared goes in the top, the x goes in the bottom. Then we have plus log base b of x to the 5th minus log base b of z cubed. And now we can do these two, and that's a plus here. And so we're going to take the product of the things inside the logarithms. These are all y's, aren't they? They'll turn into x's. That's a y to the 5th, though. For x minus log base b of z cubed. And so this last thing means put the z cubed down in the denominator, and we get log base b of b squared y to the 5th over x z cubed. So there we've condensed that into one thing. And we can do the same thing here. We can remember that log is the same thing as log base 10. 3 is log base 10 of 10 cubed, or can be rewritten as log of 1,000. So I want to take this 3 and rewrite it as a log base 10. Then I can start condensing things. So the first two things don't have any coefficients. I'll take this 1/2, that's a coefficient, and I'll put it inside the logarithm as a power. And likewise, this 2 can come in as a power on the z. And now there's a little bit of a shortcut, right? Everything that's got a plus goes in the top, everything that's got a minus goes in the bottom, and we just have one big logarithm, 1,000 times x, because addition turns into multiplication, times y to the 1/2. The subtraction turns into the division, and we get a z squared at the bottom. And again, the patterns become you get pretty used to the pattern once you've done a couple of these. So finally, the change of base property, that log base b of m is log base c of m over log base c of b. So log base 7 of 12, we can convert that into a base 17 logarithm. And so this is our claim. We want log base 7 of 12 to be log base 17 of 12 over log base 17 of 7. All right, so this base, the new base is both of these. This thing goes in the top, this base goes in the bottom. Right, and so why does that work? Well, it's the same inverse properties that we've seen before. If we set log base 7 of 12, that's some number, and we'll just call it x for now. We can convert this into an exponential equation. 7 raised to the x equals 12. But 7 is 17 to the log base 17 of 7. There's our inverse rule. And 12 is 17 raised to the log base 17 of 12. Any number is any base raised to the log of that base of the number. So that means this equation becomes 17 to the log base 17 of 7. That's this 7. Quantity of the x is equal to 17 log base 17 of 12. Because 12 is this. And now we can multiply the x through, and we get 17x log base 17 of 7 equals 17 log base 17 of 12. When we stack exponents like this, I can just multiply this exponent times the x, and we get that. Now we have the same base, but the exponents now have to be equal. So that gives me this. And so finally we get x, which is what I call log base 7 of 12, is equal to log base 17 of 12. So running out of space, go up. Log base 17 of 12 divided by log base 17 of 7. This little dividing line. So to solve this equation, right, I divide both sides by log base 17 of 7. I get log base 17 of 12 divided by log base 17 of 7 is equal to x, but x is that. So we can rewrite any logarithm in any base in terms of whatever other base we want. So log base 5 of 20, for example, you can rewrite that as log of 20 over log of 5. Or you could write it as natural logarithm of 20 over natural logarithm of 5. Grind both through your calculator, and you'll find out that those are both equal to about 1.86 and more stuff. So what's the sort of upshot of the change of base theorem, the change of base property? If you have a calculator that only does base 10 logarithms or base e logarithms, you can still find every logarithm, because if you wanted log base 5 of 20, you can convert that into a fraction involving only logarithms base 10 or logarithms base e. So for example, if we want to solve this equation, compounded monthly, where's my pen gone? Here we go. So that means our account formula for compounded monthly is that. How long will it take your account to have $600? So APRMT, we want to keep track of what all our symbols mean. A is the amount in the future, that's our $600. P is the amount that is invested, that's the $400. R is the annual interest rate, that's 0.06. M is how many times is compounded per year. 12 months in a year, that's 12. And T is a time that we don't know, because that's what we're looking for. How long will it take for money to go from $400 to $600? So we set up the equation. And we get 600 equals 400 times 1.005 to the 12t. And that's a little annoying. Here our base is 1.005, and most of you don't have calculators that have that base on them. But we can solve for t and figure out what that is. And as we did above, we solve this by isolating the exponential term. That's this part. So we'll divide both sides by 400. We get 6 over 4 equals 1.005 to the 12t. 6 over 4 is 3/2. So we get that equation. We can solve this in two different ways. We can solve it with the fundamental rule. We have a number equal to a base raised to a power. So power is equal to the logarithm of the base times 3/2, right? So that's the fundamental rule. And if we divide both sides by 12, we get t is 1 over 12 times logarithm 1.005 of 3/2. So if you have a calculator that can do this, you're in good shape, right? You just have the calculator calculate whatever this number is, and then divide it by 12, and that gives you the time. To use the change of base theorem, if you don't have a calculator that has base 1.05, you can rewrite that as 1 over 12 times the fraction log base 10, which your calculator does have, of 3/2 divided by log of 1.005. And you calculate that, and you get the same answer. And so then you can solve it using your calculator. You can also solve this with the power coefficient rule. Here's an equation. We'll take natural logarithm both sides. ln of 3/2 equals ln of 1.005 to the 12t. And what equation does that become? ln of 3/2 equals, the 12t comes out front as a coefficient. And that gives us this. And now we can divide both sides by ln of 3/2. Divide both sides by this number. And now we get 12t is equal to ln of 3/2 over ln of 1.05. The change of basis theorem rule tells me that this number, whatever it is the same as this number. And that's the same as this number. So t is 1/12 log of 3/2 over log of 1.005. And if you calculate the t for each one, t is about 6.77. And then there's more decimals. So the change of basis theorem allows you to solve any logarithmic equation, even if you have a calculator that only does log base 10 or log base e. So here are the log rules. And you'll have to memorize these because, when we get to the test, you won't be given this list. But we will do a bunch of examples of these in class. And so hopefully they'll be in your mind by the time the test comes around.